Here we're looking at the kind of problem where you have to determine if an isotope is proton-rich or neutron-rich. You also have to be able to figure out what kind of decay mode it will undergo and to be able to write an equation for that decay mode. This is a diagram from the PowerPoint notes that I went over in class. What it shows is the stable isotopes and the number of protons and neutrons that those stable isotopes have. And what you'll see is that anything in blue here is a stable isotope. It doesn't undergo any decay mode. And what you'll have here, though, are isotopes above the line and isotopes below the line. Isotopes above the line tend to have too many neutrons. That's because this is the neutron axis over here. And isotopes below the line tend to have too many protons. This is the proton axis down here. And they do have separate modes of decay that they undergo. So neutron-rich nuclei will tend to undergo beta decay. It's also called beta minus decay. And proton-rich nuclei will undergo positron decay, also called beta plus decay. The first step is to look at the periodic chart and determine, in this case we're looking at tin. This is tin 130, tin 100. So we're looking at tin, and tin has an atomic number of 50, which means it has 50 protons, and that isn't going to change. What can change, though, are the number of neutrons, which means that this mass number here is actually made up of all the isotopes of tin, and it's been averaged out for natural abundance. The assumption we're trying to make here is that if something's naturally abundant, it's probably going to be stable, and that the mass number here is at least an indication of what would be a stable isotope for tin. In this case, I'm going to say it's 118. So let's investigate tin 118. Of course, it has 50 protons, as we just pointed out. So 50 protons. And it's also going to have 68 neutrons. Now, the way we get this is to take 118 minus 50, that's 68, and that's because the mass number is made up of all the protons and neutrons. So that gives us an idea of how many protons and neutrons stable tin possesses. Our first step is to look at the problem and determine how many protons and neutrons our isotope actually has. In this case, this one has 50 protons because it's tin, and it has 80 neutrons. And again, it's 130 minus 50 is 80. Now what I want you to do is look at the neutrons. You'll see it's 80 neutrons. Over here it's 68 for the stable. I think it's fairly clear that there's too many neutrons relative to stable tin, and you would call it neutron-rich. The kind of reasoning that I'm looking for is basically the reasoning I have here. The number of protons and neutrons in the one you're talking about, and the number of protons and neutrons in stable tin. That will make up the reasoning that you'll put down here. What mode of decay will it most likely undergo? In this case, since it's neutron-rich, it will undergo beta minus decay. Now, the way that we do the equation here is we know that if it's beta minus decay, it's electron decay, which means that we're losing an electron. Electrons have this kind of makeup as an isotope. It's zero mass and has a -1 charge. Over here we've got the tin. And of course the top lines and the bottom lines have to add up. What we're going to be left with here is going to be uh, 51 and 130. And 51 on the periodic chart, you can see it right here, is Sb, antimony. And that would complete the nuclear equation for the beta minus decay. Now you might be asking, well, how do you know it's going to be beta minus decay? Well, if it's neutron rich, here's what we know. It's going to want to get rid of some of those neutrons. What we know about neutrons is that in nuclear processes, this is a neutron here, weighs 1 and has a charge of 0. It effectively can break apart into a proton and an electron. Now what you'll notice is that everything adds up. 1 plus 0 is 1, 1 minus 1 is 0. And if you think about it, it's not unreasonable to think that a neutron would be made up of a proton, which is positively charged, and an electron, which is negatively charged, and that it can release that electron and become a proton. And that's effectively what happens. If you take a look, you see that 50 turns into 51, so we're gaining a proton, and we're also losing an electron as a product. So it makes sense that anything neutron rich will want to decay in this fashion, in a way that gets rid of neutrons and turns them into protons. Now for the other one, we've got 100 SN, and that is going to be 50 protons and 50 neutrons. You'll notice it has the same number of protons as what I've got up here, but you'll also notice that it has fewer neutrons than it needs to have if it's stable. If it has fewer neutrons, it also stands to reason then that it has too many protons. So we would call this one proton rich. The kind of answer I'm looking for reasoning is pretty much included here. It shows that we have this many protons, this many neutrons in 100 tin, and for stable tin it's going to be compared to 50 protons and 68 neutrons. There's fewer neutrons than there needs to be, which means there's an excess of protons, so it's proton rich. The mode of decay will be beta plus, or positron decay. Using the same strategy as I showed you above. The particle released is a positron, which has 0 mass, but it has a positive charge on it, positive 1 charge. When we figure out what the element here is, you'll see that this is going to be 50, which means Z here must be 49, and the mass is still going to be 100, because Y plus 0 equals 100, so Y is 100. The element we're looking at here is going to be IN, or indium. And that would complete that equation. Now let's see why it makes sense for things that have too many protons to undergo this kind of decay. A proton can decay into a neutron and a positron. You'll see everything adds up here. That's a proton, 1H1. It weighs 1, it has a charge of 1. And you can see that 1 plus 0 is 1, 0 plus 1 is 1. And I think to some degree it makes sense that a proton could be thought of as being a neutron and a positron together, and then when the proton decays it turns into a neutron. So something that's going to be proton rich is going to want to lose protons and turn those protons into neutrons in order to become more stable. And that's what's happening here. You can see that it started out as being 50, it went down to 49, we lost a proton, but we also threw out a beta plus particle, or a positron, here in the product.